Hi class, we're on to Lab 9 of the semester, Equilibrium and Le Chatelier's Principle. As always, please make sure you read through the entire lab introduction and background, the experiment before listening to this pre-lab lecture video. Alright, let's go over a few major concepts that you need for this week's experiment. We have not yet covered equilibrium in Le Chatelier's Principle, so please make sure you read sections 14.1 and 14.6 of your textbook, in addition to, of course, reading the lab manual and listening to this pre-lab lecture video. Alright, so having gone through our experiment 9 in our lab manual, we have really a couple of goals for this experiment. The first goal is to observe the effect of both concentration and temperature on equilibrium, and we'll define what we mean by equilibrium in a second. And a second goal is to really experience Le Chatelier's principle firsthand. So we'll be conducting both parts, or really the goal of the experiment is really addressing both parts here. So let's first of all talk about equilibrium and what we mean by chemical equilibrium. So chemical equilibrium occurs when a reaction and its reverse proceed at the same rate. The key word here is rate, okay? So equilibrium says that the rate of the forward reaction, and what I mean by forward reaction, we have up until now we've written our reaction arrows moving forward. Equilibrium means that the rate of the forward reaction is equal to the rate of the reverse reaction. And we'll go over equilibrium in detail in lecture next week. So based on equilibrium, we actually have a rate law. In the rate law, if we abbreviate what we wrote above, rate of forward is equal to rate of reverse. Each of these rates can be written in terms of your reactants or your products and the coefficients. So this goes back to, again, appropriately balancing our chemical equation. Your rate law is always written in molar concentration. So if you just put on the side note, we always use molar concentration when writing the rate law, and we depict it in a rate law using brackets. So whenever you see brackets, that means we're talking about molarity. And remember, molarity is moles over liter. So keep that in mind. So rate is usually equal to some constant K times, for example, here if we're talking about the forward reaction, so some constant K, the rate of the forward reaction is equal to some constant K in the forward reaction times the concentration of reactant A raised to the coefficient of A times the concentration of reactant B raised to the coefficient of reactant B. Now if we look into the reverse reaction, our rate law for the reverse reaction is some constant K times the concentration of reactant C raised to the power of C, and remember brackets mean molar concentration, times the concentration of reactant D raised to the power D. So now we're reading it in the following manner. So this is the reverse reaction and this is the forward reaction. Just a side note, we always read our chemical reactions in the forward reaction, in the forward expression. So since our rate forward is equal to rate reverse at equilibrium, we can set these two equal to one another. So we have, Kf times concentration of reactant A times concentration of reactant B, both raised to their coefficients, is equal to the reverse, the constant in the reverse direction times the concentration of C raised to the power of C times the concentration of chemical D raised to the power of D. These are all the coefficients again. So we can rearrange this equation to write an equilibrium expression. And again, please make sure you're reading the textbook before coming to lab so that it makes more sense. So if we rearrange this to put our constants on one side, we can have Kf over Kr, and these are just constants. So I'm just going to go ahead and call this capital K And sometimes we show capital K and we write these this EQ at the bottom, and what we basically mean is our equilibrium constant. And we can usually look up equilibrium constants, and they're at a certain temperature. Okay, so equilibrium constants are calculated for a certain temperature. So our KEQ, our equilibrium constant, is equal to our products raised to their respective coefficients over our reactants, also raised to their respective coefficients. So this is our equilibrium expression here. Please note it's products over reactants, not reactants over products, okay? So one thing I want you to note here with this our equilibrium expression is, since the equilibrium, this KEQ is a constant, so if we write this out, since KEQ is a constant at a given temperature, all right, if the concentration of C increases, then in order to keep this as a constant, the concentration of A, the concentration of B, and the concentration of D must change in order to keep our equilibrium constant the same, okay? So if this is mind-boggling, pause for a second and think about it. This is a constant. If any one of these change, the rest have to change in order to keep this as a constant. That is the definition of a constant. So that's really chemical equilibrium for you in a nutshell. If one thing changes, the reaction has to change to really compensate for that. More so, Le Chatelier's principle actually takes this into greater consideration. So Le Chatelier's principle says if a system at equilibrium is disturbed, and we'll talk about what we mean by that in a second, the equilibrium will shift to minimize the disturbing influence. So let's take a general example. So we have here, excuse me, if we take a look over here, we have two tanks that are at equilibrium. The water levels are flowing in and out of these tanks at equal rates, okay? Now let's say we add water to tank A. That would then increase the flow, the rate of the forward direction into tank B. So notice how this arrow is now increased. So our rate of A, or rate of water flowing, is now increasing towards tank B, and it's going to increase until we've reached equilibrium, where the rates of water flowing into tank B is the same or equal to the rate of water flowing into tank A. And notice the magnitude of these two arrows are the same. So we usually show it in such manner if we have different rates. You could also have it the other way, where, for example, if we poured more water into tank B, then this would shift in that direction in order to equilibrate our expressions again. So notice here, it's not that the amounts are the same, it's that the rates are the same, okay? And it looks like the amounts are the same here, but we're really talking about rates. So the key word is rate when we talk about chemical equilibrium and Le Chatelier's principle. All right, so now let's talk about some factors that affect reaction rates. And when I talk again about reaction rates, really what I'm talking about here is equilibrium, because chemical equilibrium is dictated by reaction rates, right? Okay, so one of the factors that affect reaction rates that you're going to take into consideration in this week's lab is concentration. And what we mean by concentration here is by adding or removing a reactant or product. So this affects reaction rate. So let's take this even deeper. If a substance is added to a system that is currently at equilibrium, the system reacts to consume some of the substance. And it does that so that we go back to equilibrium. Now, in another scenario, if a substance is removed from a system, at equilibrium, the system then reacts to produce more of that substance. Alright, so that's really what we mean by concentration. Let's actually do an example here. So if we have hydrogen gas and it's reacting with iodide gas, and our system's at equilibrium, and we're showing that by the double arrow, and this produces hydrogen iodide gas. Now if we add more hydrogen gas, what's going to happen is that your system is going to shift to the right to produce more HI in order to achieve equilibrium. So this is Le Chatelier's principle in action. Now if we take the same example, and the system's initially at equilibrium, if we take the same example and let's say we're going to remove iodine gas, what's going to happen? The system will shift towards the left direction to produce more iodine so that the system is at equilibrium again. So effective concentration on reaction rates and equilibrium, and thus equilibrium, is what you're going to be doing in parts A and parts C. Temperature is another factor that affects equilibrium. So here, if the temperature of a system at equilibrium is increased, what will happen is that the system will react as if we added a reactant to an endothermic reaction or a product to an exothermic reaction. So what I mean by this is here we're treating heat as either a reactant or a product. An endothermic reaction is a reaction which uses up heat. So if you think of it as a reactant, heat is a reactant here. An exothermic reaction is a reaction that gives off heat, okay? So by having this occur, the equilibrium in this case will shift in the direction that consumes the excess reactant. And because we're talking about temperature, that could be heat or hot or cold, right? So let's take an actual example so that this might make more sense. If we have nitrogen gas reacting with hydrogen gas, the system is initially at equilibrium, and this produces ammonia gas. And this reaction is an exothermic reaction, so you could actually write heat on the side. So exothermic reaction is one where if you hold your test tube, it'll actually feel hot. So if we increase the temperature of this reaction, another way of looking at it is that, well, let's treat heat as a product, so we're increasing this amount, we're increasing T. So therefore, Le Chatelier's principle tells us the reaction will shift to the left and will produce more of these products, okay? Let's take another example. If we have nitrogen gas plus oxygen gas, this is an endothermic reaction, so it actually uses up heat, consumes heat. These types of reactions are ones if you held the test tube would go, for example, from room temperature to cold. So here, this reaction produces nitrogen oxide or nitrogen monoxide. If we increased our temperature here, what happens is your equilibrium will shift to the right to produce more nitrogen monoxide. So the equilibrium always shifts away from what was being increased. In this lab, the color of the solution depends on the relative concentration of two respective complex ions as they exist in a state of equilibrium. And I'll show you these two colors in a second. So these are really the two factors that you're going to be investigating in this week's experiment. So this is part A. Part C, temperature affecting equilibrium, is what you're going to be doing in part B. So let's dive into each one of these parts in a little bit more detail, specifically with our experiment. So part A, as I mentioned, looks at effect of concentration. Here you have a chromate ion reacting with hydrogen ions that are present from adding HCl. So initially your chromate here is a yellow solution. When we add acid to this, so when we're adding acid, so HCl aqueous, so we said that if it's aqueous, what really exists in solution is hydrogen ions plus chlorine ions, right? And if we add a base, what exists, because it's aqueous, again, what you really have in solution are these two ions, right? So sodium ions and hydroxide ions. So here we're adding a proton source or a hydrogen plus source that will change this ion into a dichromate ion, and you'll see a color change. So addition of HCl in this case is a direct source of hydrogen ions, again, because of what we have here. So that means you're increasing, in this reaction, we're increasing the amount of hydrogen ions. So let me ask you a question. By increasing the amount of hydrogen ions, which way will the equilibrium shift to counteract this change? Take a second, think about it. You're absolutely right. It's going to shift towards producing more dichromate. So this right here in lab is step 2 of part A. Step 4 of part A says, well, add sodium hydroxide, because sodium hydroxide is an aqueous solution, therefore it could supply a source of OH ions. By adding OH ions, we then are able to shift the equilibrium back to, or to counteract this change. So by adding hydroxide ions to our dichromate ion now, so one source of, well, actually let's take a step back. Because we have hydrogen ions here, when we add hydroxide ions, you're actually making water. So in this chemical reaction here, by adding sodium hydroxide, the hydroxide ions present in solution, so now we have hydroxide ions reacting with hydrogen ions to produce water. So we're indirectly increasing the amount of water. So if we're indirectly increasing the amount of water, which way will the equilibrium shift to counteract this change? Pause the video, think about it. You're absolutely right. It's going to shift to produce more chromate, and this is where you're going to see a color change. So initially, by adding protons, by adding acid, you're going to produce more dichromate because your equilibrium is shifting towards the right to produce more dichromate. When you add OH ions, you're indirectly adding water, so therefore the equilibrium, we're increasing this concentration, therefore the equilibrium is shifting to the left, and therefore you're going to see a color change of yellow in your test tubes. In part B, we're looking at effect of also concentration and temperature. So in part B, we have a chloro complex and an aqua-chloro complex. One's blue in color, one's pink in color. So here really this is relating to step 2. If you can print this in color, bring it to lab, that'd be great. Otherwise, write the colors down. So here in step 2, this reaction is an exothermic reaction, so that means we're really producing heat as a product. Step 3 for this reaction, we're adding HCl to one of the test tubes containing this aqua complex, right? So we started by having this pink aqua complex, and we're increasing the presence of hydrogen ions. So if we're increasing the presence of hydrogen ions, that means we're decreasing the presence of, we're adding HCl, so therefore we're going back and producing this chloro complex blue, and that's why you'll see a color change, okay? In step 5, And I'm going to leave these questions for you to answer because this should be in your notebook. So I want you, after conducting this experiment, I want you to actually tell me which way does the reaction shift, the equilibrium shift, excuse me, to the right or to the left based on our addition of HCl or heat. So in the first part, we're changing our concentration by adding HCl. In the second part of part B, which are steps 5, we're changing the temperature. So we're heating one of the test tubes containing the aquo complex. So now we have our aquo complex. We're heating the test tube, therefore we're increasing temperature. And if we're increasing temperature, I want you, based on your observations, tell me which way the equilibrium shifts to counteract this change. And again, in your notebook, I want you to actually write down your reaction arrows based on what happens. So now in step 6, instead of heating, we're now going to cool our test tubes. So remember, heat is a product, so in one step we've increased it, so this is in step 5. In step 6, we're cooling it, so therefore we're decreasing heat. Again, I want you to note, obviously color changes, always make observations, but I want you to also write the reaction in your notebook and show which way is the equilibrium shifting to counteract this change. All right, in part C, the last part, we're looking at the effect of solubility. So you have a saturated solution of sodium chloride. So saturated solution of sodium chloride, we've reached saturation. Any extra sodium chloride we have will no longer dissolve. So what we actually have in lab is a supersaturated solution of sodium chloride, and we're calling it brine. So you're going to see a beaker in lab where you have aqueous sodium chloride present, which we already know that means you have sodium ions present and chlorine ions present, but you're also going to find salt at the bottom. So this is a saturated solution of sodium chloride. We've already exceeded saturation, and therefore some sodium chloride is no longer capable of being dissolved with the amount of water that we have. So we have our following reaction here. It's at equilibrium, so we have forward and reverse rates of reaction equal to one another. So in step 1 of part C, what you're doing is you're going to add HCl to this reaction. And by adding aqueous HCl, so remember, anything aqueous exists as ions in solution. So by adding hydrochloric acid, you're actually adding a source of chlorine ions, which means you're increasing the amount of chlorine ions in this reaction above. So based on that, I want you to tell me which way will the equilibrium shift to counteract this change. And again, make note in your lab notebook on which way it'll change. So those are parts A through C of your experiment. This experiment's really neat because you actually see a different nature of chemistry going on, and you're really affecting equilibrium, and you're able to control, well, which way will the equilibrium shift to compensate for that change. Now let's actually do an example of this, a written example of this. So we have a reaction here where it's the formation of ozone. So when oxygen reacts with heat, we produce ozone gas. So formation of ozone is an endothermic reaction, and it's endothermic because it's absorbing heat. Exothermic if it produces heat. So here I have a series of questions for you. What effect does each of the following changes have on equilibrium? So what effect does adding ozone have on this equilibrium? So this reaction is in equilibrium. We show that either by this double arrow, or you can have 2 arrows. So this is 2 ways of showing equilibrium, okay? What happens if you add oxygen? What happens if you raise the temperature? What happens if you lower temperature? So keep in mind what Le Chatelier's principle says about changes to the equilibrium and how we compensate, counteract those changes. Okay, so, all right, I'm going to rewrite my chemical reaction here so that I can better figure out, well, which way will the equilibrium shift? That's pretty much what I'm asking you. So I want you to pause this video, take a few minutes, solve this on your own, and then come back to this video. All right, I'm going to assume you pause this video. So what happens if we add added ozone. So that means we're increasing the concentration of ozone. So when you increase the concentration of ozone, that means we're going to produce more O2 to compensate for that change. So therefore, your reaction will shift left. Another way of saying this, it's going to favor the reactants, or more reactants will be produced. Now, if we add oxygen, so now we're in an example, so part B says, well, let's add oxygen to this reaction. So if we add oxygen to this reaction, you're absolutely right. It's going to shift, equilibrium will shift right, which means your products are now favored, meaning you're going to produce more products. Okay, what happens if we raise temperature? So part C, we're increasing temperature. Remember, temperature, we're treating it as a reactant or a product. So in this case, temperature is a reactant. So when we increase temperature, yep, you're right, you're shifting your equilibrium to the right. So therefore, we're favoring products. Now, what happens if we decrease temperature? If we decrease temperature, the equilibrium will shift in the direction to compensate for that decrease. So therefore, it's going to shift left. So therefore, reactants are favored. Okay, so that's a written example for you of how Le Chatelier's principle is taken into consideration on paper. Again, this experiment's great because you actually see equilibrium and Le Chatelier's principle in action by affecting things like solubility, concentration, temperature, etc.